Good evening and welcome again to Basic Science Lights the Way. Tonight, three scientists will discuss what their research has revealed about our solar system's largest planet, Jupiter, from the fluid dynamics of the Great Red Spot to the mysterious magnetic tornadoes at its poles. So, whether you're a seasoned space scientist or you simply have a passion for the night sky, prepare to be amazed as we decipher the secrets of our solar system's fifth planet. Jupiter's enormous size and enigmatic beauty have captivated stargazers for centuries. Astronomers have studied its most recognizable feature, the Great Red Spot, since the 1870s. If seen from the side, this king of solar system storms would have a tiered wedding cake structure with high clouds at the center cascading down to its outer layers. Astronomers have noted that it is shrinking in size and becoming more circular, yet with a diameter of 16,000 kilometers, it is still comfortably larger than the entire Earth. Our presenters are also a family of scientists, having worked together over many years collectively, and are a great example of how Berkeley's research enterprise is, at its core, a human endeavor, a continuous unfolding of questions, discoveries, and mentorship passed from one generation to the next. This lineage of scientists we are featuring tonight is a powerful reflection of UC Berkeley's deepest investment, not just in ideas, but in people. It shows how Berkeley nurtures talent, fosters collaboration, and creates a legacy where knowledge is not only advanced, but shared. In this way, the university doesn't just produce breakthroughs, it cultivates a living, evolving community of thinkers who carry each other and the world forward. Now it's my pleasure to introduce our moderator for this evening. Mike Wong is a planetary scientist at the Space Sciences Laboratory here at UC Berkeley, researching planetary atmospheres and origins with a focus on giant planet clouds and chemistry. Mike's analysis of data from the mass spectrometer on the Galileo probe launched his interest in cloud-forming gases in Jupiter's atmosphere. He has used Cassini infrared spectra to detect ammonia ice signatures on Jupiter and Curiosity rover data to study isotopes and seasonal changes in the composition of Mars' atmosphere. He was selected as a Juno participating scientist, studying Jupiter's lightning, convection, and volatiles. He led Hubble and Gemini imaging programs in support of the Juno mission and is a founding member of the multi-cycle Outer Planet Atmospheric Legacy, or OPAL program that conducts annual observations of the giant planets with Hubble. He has served on national level committees, such as the most recent Planetary Decadal Survey conducted by the National Academies of Science, Engineering, and Medicine. Thank you for being here this evening as our moderator, Mike, and let me turn it over to you.
Thank you, Dean Kahn. I'm excited to be here with my multi-generational science family. Long ago, when I was an undergraduate student at Cal, Tsubota was a professor who introduced me to research and guided me to write my first science article. Eventually, I came back to work with her, then met Phil Marcus as a researcher here, and finally mentored undergraduate Troy Tsubota on the Jupiter Journal article that is the basis for his presentation tonight. As Dean Kahn mentioned, I'm part of research teams for NASA's Juno and Mars Science Laboratory missions, and I co-founded the Hubble OPAL program, which images all 4 giant planets each year. Here, we compare simultaneous Gemini infrared image with a visible light image from Hubble that was part of a multi-observatory campaign to look at Jupiter at the same time as the Juno spacecraft passes over the planet's atmosphere. This helped us to reach new levels of understanding of this great planet and its turbulent atmosphere. Most of us have thought that the upper clouds of Jupiter, where subtle color changes distinguish pale zones and darker belts that you can see in this Hubble image, are made of ammonia ice, with deeper clouds of ammonium hydrosulfide and deeper still water ice and liquid water clouds. This has been widely accepted since the 1960s, but from time to time we discover little things, studies, and new observational campaigns to figure out what the clouds really are. One of the latest approaches was even pioneered by a citizen scientist, so there's really a wide range of people helping us to unravel the secrets still lying within our solar system. At the end of each talk, we will take questions from the audience, so please add your questions in the chat. Now it's my pleasure to introduce our first speaker, my former student researcher, Troy Tsubota. Troy is a fourth-year undergraduate student at UC Berkeley, majoring in physics, computer science, and applied mathematics. Troy currently conducts theoretical physics research with Professor Joel Moore and Professor Edgar Knobloch. Previously, Troy researched outer planet atmospheres in my lab. Outside of research, he has taught calculus and linear algebra as a teaching assistant and received the Outstanding Graduate Student Instructor Award in 2024 for his teaching. He has also been involved in several science organizations, including the UC Berkeley Society of Physics Students and the Bay Area Scientists Inspiring Students, for which he taught physics to local elementary school students. This fall, Troy will be attending Harvard University to pursue a PhD in physics. Troy, thank you for joining us this evening. Can you share some of your research with us?
Thank you, Mike, for the introduction. Today, I'm going to be telling you all a story, and it's a story of this image here. So what you're seeing here is a false color image of Jupiter. This is not a typical color you might see from Jupiter, and it's angled in such a way so we can see the South Pole better compared to usual images. And you might notice, for instance, like the Great Red Spot that the very famous Great Red Spot is here in blue. I won't be talking about the Great Red Spot today. I will instead be talking about this little dark patch in the South Pole, which we're going to call the dark polar oval. Now, interestingly, there's a lot of science baked into this one picture here that will explain what this oval is. But in order to understand this, we need to take a step back and think about how we actually built and constructed this image in the first place. And so just as a comparison, on the left here is probably what you would imagine as a typical Jupiter image. And so you can see the side-by-side comparison of the colors that changed and also the angle that changed so that we can better see the South Pole and that dark polar oval. So how did we construct this image? Well, we started with Hubble Space Telescope data. The Hubble Space Telescope has been around since the 1990s. It's in low Earth orbits, and it's taken plenty of fascinating images of the cosmos, many of which have become famous, like this nebula here on the left and this picture of galaxies on the right. Hubble is also very good at taking pictures of the planets, which is the data that we use for this study. So how exactly did we do this? Well, Hubble doesn't quite work the same way as our cameras on our phones. What you have to do is you have to pick a specific wavelength that you take an image of Jupiter with, or of any astronomical object. And so in our study, we use ultraviolet light for our images. And so we apply that filter to Hubble, and what comes out is not a nice colorful image of Jupiter. It is a black and white image of Jupiter, where more bright pixels mean more ultraviolet light, while dark pixels mean less ultraviolet light. And so then we can pass that through, Photoshop or whatever, and turn all those pixels to be red. And I want to emphasize here that this red has nothing to do with the red that is actually coming out of Jupiter. It is the ultraviolet light coming out of Jupiter that we are coloring red. And for our study, we didn't look at just one ultraviolet wavelength, we looked at 3. And so we took another one, we made it green, and we took a third one and we made it blue. all of these three are just different ultraviolet wavelengths. We can't see any of these with our eyes. But now, with a little Photoshop, we can turn it into red, green, blue, and put it all together, and we have our image of Jupiter. And so, as I mentioned, there's a lot of science in here because we know the exact wavelengths that we got. And before I dive into exactly explaining what this dark splotch here is in the South Pole, I want to show you one other thing, which is what happens if we, like this is one image, this is a static image. What happens if we were to watch this over time? And so what I have here is that dark splotch, but now it's black and white because this is more of the raw data. And what I have here is a quick animation of what this dark splotch is doing across like a period of a day or so. And what we can see is this dark splotch is actually rotating. And so we can take this observation and in conjunction with the UV image that I've described, and we can kind of boil this down to three observations about this dark spot. Number one, it is dark in the UV, as I mentioned. The second observation is that it's located in the South Pole. And the third observation, as I just showed in the animation, is that it rotates. And so using these observations, as scientists, we can start to think about what is a phenomenon that can explain what we see. And so I'm going to break this down step by step to understand what we're looking at. So let's start with the first one, the observation that the dark spot is dark in the UV. So what does that tell us? Well, what does it mean to be dark? Well, there are particles in Jupiter's atmosphere. And there's UV light that is coming through the atmosphere, which is what we see. And if there are not a lot of particles, the light can come right into the Hubble Space Telescope camera. If there are a lot of particles, well, there's not going to be as much light coming out. So that's why it's dark, is that if it's dark, there are more particles there. But because it is UV, that doesn't just tell us there are more particles, that tells us where the particles are. And to explain that a little more, I have a picture here of, or a diagram here of Earth's atmospheric layers. And we're kind of used to the atmosphere being like the troposphere, is more what it's more specifically called, which is this lower atmosphere. But there are plenty of higher layers of the atmosphere that all have different properties. So you have the stratosphere, then the mesosphere, and then the thermosphere. And this thermosphere extends very far up into what we would think of sort of intuitively as space, but that is still part of Earth's atmosphere. So we have these different layers on Earth, and it turns out there's also these different layers on Jupiter. And so what the UV light allows us to do is to really extract information about the stratosphere. So just like an X-ray allows you to peer through your skin and to see the bone, we can take UV light to look at the stratosphere. And so what we're seeing is not only there are more particles, but there are more particles in the stratosphere in this dark oval. And so that is really the power of seeing this in the UV, and is something that we weren't able to easily see in other wavelengths. So we know it's a stratosphere effect. And so this observation tells us there are more particles in the stratosphere. The second observation is that it's located in the South Pole. And so we can think, what kinds of things happen in the polar regions only on Jupiter? Well, what are some things that only happen in the poles on Earth? What kind of atmospheric effects? Well, one thing we know very well is the northern lights or the aurora. These lights only appear in the north and south poles, and it's this very interesting phenomenon, and it occurs because Earth has a magnetic field. Specifically, there are charged particles like electrons that are flying around the magnetic fields and are traveling along these magnetic field lines and slamming into atmospheric particles on Earth. And that's what creates the light. And so Jupiter also has a magnetic field. And if we look a little closer at specifically where that dark polar oval is, it is actually exactly where the magnetic field lines come into Jupiter. And so based on the location, we're able to determine that, hey, maybe this dark oval is connected to the magnetic fields. The third observation we have is that it rotates, as I showed in the animation. And so we have a lot of particles, we have this magnetic field, maybe there's some kind of magnetic storm that's going on. Now, I'm no expert in magnetic fields or magnetic storms, and so we talked to some experts that are in Jupiter magnetic fields, and they said, hey, we noticed something very interesting in a previous study, which is that we get this storm in the thermosphere of Jupiter, which is caused by the same reason aurora light up. We have these charged particles in the magnetic field that are causing the storm in the thermosphere of Jupiter. And so this is what the experts told us, that, hey, there's previous work done that shows that the storm is here in the thermosphere. Now, our work says there are more particles in the stratosphere. So then it's a reasonable, hypothesis to think, hey, maybe it's like this tornado that starts in the thermosphere due to the magnetic field and extends into the stratosphere and causes these extra particles to show up. And we looked at some other competing hypotheses, but every one of our observations agrees with this idea of a magnetic tornado because it is dark in the UV, is located in the South Pole, and it rotates. And this is really interesting because compared to, say, the aurora, which are these nice lights, Jupiter's magnetic field is so much stronger that it's causing this, tornado to show up, which I think is very fascinating. And so I hope I gave you a little insight into how this image was constructed and what science is going on underneath that dark polar oval. Thank you very much, and I'm happy to take questions.
Well, thanks, Troy. If anyone has any questions about how we did this work or what we found or anything about Jupiter, go ahead and put those in the chat. So it looks like we have one question, which is, are you the first to discover these dark ovals?
So I am not the first to discover these dark ovals, but our study was the first sort of systematic study of these. So there was this dark patch that showed up in some studies from the late 1990s, and Cassini, which is well known for Cassini is well known for the what is it, Saturn studies. It actually did a flyby of Jupiter and saw this dark oval in the North Pole. What we've done is a more systematic analysis of this and actually a understanding more deeply how this is connected to the magnetic field.
Cool. A lot more questions are pouring in. We have one here from Jameson Rollins. And he wonders whether the strong magnetic field implies that Jupiter has a large iron core.
Yeah, so I'm no expert on magnetic fields, as I mentioned. My understanding is there's no iron. Well, yeah, I'm not actually an expert on that, so I may defer to other people on that.
Well, I to chime in a little bit that Jupiter is so massive that the extreme pressures in the interior actually cause hydrogen itself to become metallic. So the question is correct that you need some sort of conductive material in this rotating interior to generate a magnetic field, but in this case, it's hydrogen instead of iron. Let's see. Megan Schwartz wants to know whether the tornado is related to the rotation of Jupiter.
Yes, so it's a pretty subtle thing that happens. What's going on is that Jupiter has a rotation, just like Earth rotates 24 hours per day. And but Jupiter actually rotates pretty fast. It rotates at 10 or 11-hour period. And there's this interesting friction that goes on between the speed at which the magnetic field is rotating and the speed at which the atmosphere is rotating. And those are not aligned properly. And it's this friction that occurs between the magnetic fields and the really the particles in the magnetic fields and the atmosphere that's generating the storm.
Cool. Mark Wegner wants to know, how was the orientation of the image done? You showed a view kind of looking down at the South Pole, but most telescopic images are from the side.
Yeah, that's a great question that I wanted to explain a little more, but I had a short amount of time. But what we did is we took, as I mentioned, Jupiter, rotates every 11 hours or so. If we take a lot of images of Jupiter over a long period of time, we can kind of construct what is close to a 3D reconstruction of Jupiter, and then we can project it sort of along any and kind of view it from any angle we want, sort of synthetically. And even then, the pole is still hard to see, as you mentioned, that it's viewed from the side, so it's hard to look at the pole. But Jupiter and Earth are not perfectly aligned horizontally. There's always a little bit of variation. And so that image we constructed was at a particular observation where that variation can see the South Pole slightly better than what we normally could see. But that's a great question. It's not one image that we took to get that image.
Okay, I think we have time for one more question, and then there's going to be more questions for all the speakers at the end. But James McFarland wants to know, is there also such a thing occurring at the North Pole?
Yes. So there is also a northern dark oval, and that was actually kind of like the first major observation of this this tornado. However, what we noticed, what we found in our study, this is sort of the big study we did, was that the South Pole dark oval appears much, much more than the North Oval. And that's actually further evidence that it's a sort of a magnetic effect, because the magnetic field is structured a little differently in the South Pole and the North Pole, which makes it more favorable for these storms. And specifically, like in some sense, the energy is more highly concentrated in the South Pole, which allows you to get these storms to occur more frequently. But yes, they do show up in the North Pole.
Thanks again, Troy. We will have a few minutes at the end for more questions again. But now we'll move on to our next speaker of the evening, Professor Philip Marcus. Phil Marcus is the Tien Modoc Chancellor's Chair in Engineering and Professor of Fluid Dynamics in the Department of Mechanical Engineering. He's the former head advisor for the UC Berkeley Graduate Program in Applied Science and Technology and head of the Department of Mechanical Engineering's Laboratory for Computational Fluid Dynamics. His research spans a range of fields and incorporates the development of new algorithms for scientific computing. As a computational physicist, he seeks out collaborative studies with experimentalists of chaotic and nonlinear flows and astrophysical fluid dynamics, including planetary atmospheres, star formation, and the particle-laden fluid flows responsible for planet formation. His current research in algorithm development, astrophysical fluid flows, and internal gravity waves is supported by NASA and the National Science Foundation. Phil, please tell us about your work.
Thank you. Let me share my screen and let's see if hopefully we can. So I'm going to talk about everybody's favorite spot, or at least my favorite spot, which is the Great Red Spot, which I'll call the GRS, all right, for Great Red Spot, and talk about this spot and possibly a spot remover. Okay, so the first published observation of perhaps the red spot or of some red spot was by Robert Hooke, the same Hooke that did microscopes and springs, and that was in volume 1, number 1 of the Proceedings of the Royal Society way back in 1664. Being astronomy and physics, of course, it was immediately controversial, and 1 year later, Cassini published a claim that no, he saw it first. And then we zoom up to 2024, and our colleague, Agustin Sanchez La Vega, claim that by looking at records, including those in the observatory at the Vatican, that red spot had disappeared. It was not reported for several hundred years. And so we now have a different red spot, and that red spot has been continuously seen since 1857. So maybe the red spot is 150 years old, maybe it's 350 years old. It's not at all clear, but it is at least an old object and a controversial object. Now, we didn't know that much about what the red spot really was until about 1979, when the two Voyager spacecraft approached Jupiter. Jupiter rotates once every 10 hours, and so once every 10 hours, the red spot is at high noon, and an image was snapped, and the images were all put together to make a wonderful movie. And we can see that the red spot is, in fact, a swirling in a counterclockwise direction mass of fluid. It's about 26,000 kilometers long when Voyager went by it, and about half that height. It exists in a very turbulent and fluid atmosphere, and it's surrounded by a bunch of east-west jet streams. If I take this last image and lay it out into a rectangle, what I can see is my red spot right there. That's the red spot. And it has this magenta line, which maps out the east-west velocities, which are the zonal winds. So there's a dozen jet streams on Jupiter compared to basically 2 on Earth. So this red spot is strongly influenced by the fact that there is a jet stream moving from east to west just north of it, and one in the opposite direction just south of it. We developed in our laboratory and with our colleagues here in Berkeley a method that allows us to take very precise extractions of the velocity in the atmosphere based on sequences of the photographs of the clouds. And here is a picture that which is a subset of the 500,000 velocity vectors that were extracted of the red spot. So the north-south direction is the vertical, the east-west direction here, the longitudinal direction is my horizontal direction. And the red spot is this swirling river of fluid about 100 meters per second is what it's going at. But the center of it is hollow, barely any motion at all, or sometimes fluid rotating in the opposite direction. So we call that phenomena hollow. This is a hollow vortex because it doesn't have anything going on in its interior. Very, very rare to have a hollow vortex. You don't get them in the laboratory. You don't get them in your bathtub. You don't get them in the Earth's atmosphere or ocean. So this is a real signature, almost unique signature that Jupiter's great red spot has, and we want to understand why it is hollow. What is the importance of that physics? In fact, some of the things that we want to understand on Jupiter is why does it last so long? It takes about 6 days for the fluid at the outer part of the red spot to make one rotation. That's a turnaround time. It lasts for 1,000 turnaround times. That's really long. Hurricanes don't last that long. Tornadoes don't last that long. Why is it so long-lived? Already mentioned, why is it hollow? And we only have, right at the visible cloud layer where Voyager and Hubble takes its images, this is the layer, right? This one little layer in the atmosphere, in the troposphere, where we have velocity measurements, and we want to know what is the 3D structure of it. Does it go way up high? Does it go way down low? Are we only seeing the tip of the iceberg and the most interesting part of it is not visible to us? And also, is there something unique about the Great Red Spot so that if we do some numerical simulations and capture its winds and temperatures, that we can say, yes, we know for sure what the 3D structure is? So let me just give you some basic physical ideas. As I said, the red spot, right, indicated by this schematically, this red oval, and the black velocity vectors inside of it, it's situated it's sandwiched between 2 jet streams. And these jet streams tug on it. If I make the jet streams longer, stronger with respect to the velocities inside the vortex, it will tend to stretch it out in the east-west direction and make it more and more oblong. If I make the swirling velocities inside the red spot stronger and stronger and compared to the surrounding jet streams, then it will become rounder and rounder. Okay, so there's two competing effects here. So this is kind of a clue for where I want to take my research. So here's a spoiler alert and a philosophy of your check on life. The east-west diameter of the Great Red Spot, both the old one and the new one, if they're separate things, shrank in the 1600s, and it's shrinking today. Okay, so one might say, oh no, a decrease in the vortices areas would cause the diameter to shrink, and therefore the diameter of the red spot and the area is decreasing. Oh, it's the red spot's dying. On the other hand, if you're maybe an optimist, an increase in the strength, the swirl of the vorticity inside the red spot causes it to become rounder and rounder, and its east-west diameter shrink according to the observations. So therefore, its strength in terms of its vorticity is greater, so the red spot is thriving. So I can leave it up to you for the moment. Is the red spot half empty or half full? Okay, so my thing is doing three-dimensional numerical simulations. I can do wings, I can do all sorts of objects. The red spot is very hard to simulate in 3 dimensions rather than doing a 2-dimensional approximation because its environment changes so much from its bottom to its top. So what you see here is a numerical simulation where we start off with a guess of what the red spot looks like. We put on the equations of motion and turn the computer on and see what we get. And what we get is the following. So the color here is the vorticity. And I haven't started with a hollow vortex because all my experiments in 2 dimensions say, boy, hollow vortices are always unstable. They fall apart. They turn themselves inside out. So the vertical direction here is the latitude. The horizontal slice of this is the longitude, and you're seeing our 3D numerical simulation sliced at the height of the clouds where the Hubble Space Telescope took its measurements. So we turned the thing on, and it wasn't a very good guess at equilibrium, so it gets real stretched out, but it starts to become rounder and reassemble. Some of the vortices that broke off start to come back together. And what we find in this, our very first numerical simulation with our brand new code, once it had been validated, a non-hollow vortex became hollow. You can see that the color of the pixels is lighter at the center. And so this came as a real surprise to us. Okay, what's more interesting perhaps is looking at our best fit to the data where our temperatures agree with those that were measured by the space telescopes, and the velocities agree with the hollow velocities measured by Hubble. And the vertical axis of these 2 images is the vertical direction in the atmosphere. And notice it's measured in hundreds of kilometers. The horizontal direction, we've gone through the center of the red spot, and one is the north-south distance and one is the east-west direction. So you get 2 different perspectives on this. This is what the vorticity, the swirl, read as a color, looks like as a function of height and horizontal position. It is kind of a Christmas tree-shaped ornament with the biggest, darkest regions of red well below the region where it says 0. That is the height in the atmosphere where the Hubble Space Telescope makes its measurements. The green horizontal dashed lines is where the James Webb Space Telescope makes its velocity measurements. And in between those 2 lines is where we have some direct measurements of the temperature of the Great Red Spot. So you can see between the black and the green lines, it is hollow. Not only does the red disappear, but it actually rotates in the opposite direction. So this is a 3-dimensional numerical simulation of our red spot. Now, what we found was we thought we could make many, many simulations that produce the temperature and velocity fields as measured by the space telescopes. And that turned out not to be true. The temperature measurements from the James Webb Space Telescope put a severe constraint on where the top of the red spot is. It tells us where in the atmosphere it is. The velocity measurements puts a lot of constraints on what that shape of that red spot is going to be. And what we discovered, if we wanted to meet those velocity measurements and those temperature measurements, we tried and tried and tried with our numerical simulations. We only got 1 vortex ever that could do that. So we think this is it. This is the unique vortex that really tells us what the three-dimensional structure of the great red spot is in the atmosphere. And we see that we're seeing the tip of the iceberg. Most of the action is below the visible cloud level. Also, to our surprise, we didn't use any of the observations of the Juno satellite, which is still orbiting Jupiter. And this Juno satellite measured the anomalous gravity due to the great red spot, and it measured some temperatures below the cloud decks. And our numerical simulations agree completely with those observations. So we think we've got now a unique understanding of what the red spot really looks like in terms of its three-dimensional structure. And let me say, that's not the end of our study. It's the beginning of our study. Astronomy is an observational science. You don't get to go into the laboratory and tweak knobs like you do in other fluid dynamics experiments in our laboratories here. So but now that we have the red spot simulated in the computer, we can change as many knobs as we want in the computer. We can let it drift upward in the atmosphere, downward in the atmosphere. We can make the jet streams weaker or stronger. We can add different kinds of clouds, and we can see how it changes. Does it shrink? Does it grow in size? So this isn't the end of our study. This really is the beginning of our study. So I thank you for your attention.
Thank you, Phil. We only have time for maybe one question, and I really like this question. From Francois Sorgen. I'm going to rephrase it a little bit, but what would happen if the Great Red Spot were at the equator of Jupiter?
You wouldn't get a red spot at all. The equator of Jupiter is like the equator of Earth. There's no sense of the planetary rotation there because the rotation vector, which goes between the South Pole and the North Pole, is perpendicular to the surface or perpendicular to a height of constant pressure. And so the effect of rotation just ceases to exist. The red spot requires rotation, just like a hurricane requires the rotation of the Earth to exist. So though you think of the hurricane as a tropical storm, it cannot happen within about 8 degrees of the equator. So the same thing would happen for red spot-like objects on Jupiter. The equator is a forbidden area.
All right. There's another question from Jameson Rollins, but he asked a question last time. So let's move on to the next speaker. And we can come back to Jameson's question later if there's time. So our final speaker of the evening, please welcome Imke de Potter, professor in the Departments of Astronomy and Earth and Planetary Science. Imke de Potter was the chair of the astronomy department from 2010 to 2015, during which time she directed building New Campbell Hall, which houses the astronomy department. Although she is emerita now, she is still the faculty liaison with the Breakthrough Listen team and very active in research. She is well known for her work on Jupiter's synchrotron radiation, for which she received the Ursi John Howard Dellinger Gold Medal in 1984. She led a worldwide campaign observing Jupiter's radio emissions during the impact of comet Shoemaker-Levy 9 with Jupiter in 1994. This work has led to a detailed investigation of the effects of impacts on the magnetospheric environment of the planet. She explored the limits of what the adaptive optics on the Keck telescope can do by observing the giant planets in their rings and several of their moons. Recently, Professor de Potter's team observed Jupiter as well as its rings and the moons of Io and Ganymede using the new James Webb Space Telescope. JWST's ability to detect mid-infrared light gave her team access to different layers of Jupiter's atmosphere, ones they have not been able to previously explore using Earth-bound or space-bound telescopes. Today, she will talk a little bit about her team's work on radio observations of Jupiter. Imke, thank you for joining us.
Thank you, Mike, for this nice introduction. So in the previous talks, we heard about Jupiter's clouds, the aurora, and the Great Red Spot, which are all very beautifully seen on this false color image of Jupiter that we took with the James Webb Space Telescope. So we will now dive into Jupiter's atmosphere through the clouds to see what is hidden below the visible cloud deck. So we do this by observing Jupiter at radio wavelengths, where the clouds are transparent, and the depths we probe depends upon how much ammonia gas is in the atmosphere, since ammonia gas is the main absorber of radio light. So in the visible and the ultraviolet, we see Jupiter because sunlight is reflected off the cloud layers. At radio wavelengths, we see thermal radiation from Jupiter itself. That is, we receive emission because Jupiter is warm, just like you see infrared emission from warm people and animals. Because the temperature increases with depths, as shown on this sort of faint line over here, Jupiter will be brighter the deeper you probe. So at the wavelengths of 1 centimeter, which is over here, we probe down into the upper cloud layer, the ammonia ice cloud. And at longer wavelengths, at 6 centimeter, we probe down into Jupiter's water clouds. So over the past kind of half century almost, I have studied Jupiter's radio emission, and it was only in 2014 that we were able to, for the first time, to produce a full radio map of Jupiter. So at the top here, we see a 1 centimeter or 22 gigahertz map constructed from data from the Very Large Array, or the VLA, in New Mexico. So here we look down into the ammonia ice cloud, and you see very clear variations in brightness, temperature, a very hot, as we call, radio hot belt. We see many features, the radio hot belt is here. We see many features are small vortices. We see the great red spot here, an oval referred to as oval BA. So the bottom picture is a visible light map that is put together by amateur astronomers. And this one is actually interleaved with a VLA 2 centimeter map taken at the same time. And so when you look carefully, you can see many, many features, similar features in the visible and the radio, which is indicative of variations in the ammonia vapor and cloud concentration. So at the top now, I show a 6 centimeter map, essentially probing down into the water clouds. Here we simply do not see very much, except for these very large plumes over here, these dark features, which bring up ammonia gas from the deeper atmosphere up to above. And we still see that radio hot belt with so-called hot spots. The great red spot is also still barely visible and shows that it's definitely there below the water cloud, as Phil just mentioned in his talk. So this is a composite, VLA composite map of 3 wavelengths. The red shows the 3.5 centimeter and blue a 1 centimeter. So this map shows actually quite clearly that overall most features are very shallow. They happen in the weather layer down to maybe 10, 20 kilometers below the visible cloud deck. Only where we see red do we look down into the water clouds, like in this radio hot belt and around the great red spot. So from these data, we derive the ammonia distribution in the atmosphere from the top down to about 100 bar level. We clearly see a lot of ammonia gas in the equatorial zone up to high altitudes, but other than that, here in the North Equatorial Belt, the radio hot belt, we see a much less ammonia gas. But what is kind of striking is that we see that ammonia seems to be depleted relative to deeper layers everywhere, and that has been quite puzzling to solve. Well, then Juno came along. So Juno cannot make global maps like the VLA. It observes over a very limited range of longitudes, as shown here by the red ellipses. But over that very tiny region, it probes down into the atmosphere to much, much deeper levels than the VLA can, because Juno observes at much longer wavelengths or lower frequencies. And that is shown here on the left side. We see 6 frequency channels. Juno probes down from the top, the ammonia ice cloud layer, all the way down to several hundred bars. And on the side, we can see, for comparison, the depths that the VLA is probing. So my student, Chris Mockel, used 12 of these Juno orbits, put them together, and he derived the ammonia abundance based upon the Juno data. And he showed that ammonia is actually depleted all the way down everywhere, except in the equatorial zone, down to about the 30 bar level. So way deeper than we had seen before from the VLA data. And that was not at all expected and extremely puzzling. But as I will show you next, some large storm systems on Jupiter may give us the answer. So in December 2016, amateur astronomers discovered a bright region in the south equatorial belt, this tiny, tiny little thing, and that evolved into a very large storm system. So fortuitously, we observed Jupiter a few days later with the Atacama Large Millimeter Array in Chile, ALMA, and detected this storm. We also detected it in Hubble Space Telescope images a week later. So here is the storm in Hubble Space Telescope, and this here is in the ALMA data. So this is the source of the storm, not visually very appealing, but it does show us that ammonia is being brought up from the deep levels, like in the sketch here, from deep levels up. And when it reaches the higher altitudes, ammonia gas will freeze out and the ammonia dry air will descend around the spot, showing us this radio bright region around the dark spot. So a few weeks later, Juno actually, its tiny footprint happened to cross this storm, and that is shown over here. So things have changed a little bit, and it didn't quite capture the core of the storm, but it does clearly show some in the blue parts where it's cold and red parts where it's warm. So for his PhD thesis, my student Chris Mockel derived the structure of this storm, and he basically saw that ammonia vapor concentration increased with altitude up to the ammonia cloud layer. But basically, it's essentially what was shown before, that ammonia is brought up, it will condense out, and then the ammonia dry air is descending in these red areas here. But most remarkable, however, was that he found that ammonia gas was depleted to well below the water cloud, well below to where this storm was triggered. And that was quite puzzling. Although one could imagine that ammonia ice, once formed up in the atmosphere, would fall down just because of gravity, and thereby removing ammonia from the upper layers. But it was pretty inconceivable to see how these ice particles falling down would fall down to well below the water level before it would evaporate again, unless these things would be really golf ball-sized chunks of ice. Now, initially, Chris and I were very skeptical about the so-called mushball theory, but now we think that we actually have seen the first observational evidence that this theory may be right. So in very simple terms, what happens is the following. Very strong updrafts during storms can lift tiny water ice particles high above the clouds. And while rising, this water ice will mix with ammonia vapor to form slushy ice balls. So they continue to grow while rising and then while falling down, like hailstones on Earth. And eventually these mush balls become as large as softballs. They keep on falling down, and once below the water cloud, they start to evaporate because the temperature is higher. But since they are so big, it takes them another 100 kilometers or so below the water cloud before they are fully evaporated. So there are probably many of such storms, as seen from the zillions of lightning storms that we have seen with Juno. And we think that all these storms together cause ammonia to be depleted globally down to these greater depths. So although the theory had been around for about 5 years, Chris and I were skeptical about it. But we now have the first observations that actually show that the theory is probably right. So we find that observationally, ammonia and water cycles are coupled, and we show how storms redistribute the energy and trace gases in the atmosphere. And this confirms the storm's crucial role in heat transport within the atmosphere, and it also helps explain the global depletion of ammonia down to about the 30 bar level, as seen from Juno's radio observations. So these 2 papers were recently published, the one both about which I just talked about, and there was a press release on Tuesday about this work. Thank you for listening.
Great. Thank you, Imke. And I see that Maria has placed a link to this press release in the chat, if anyone would like to see that. Let's see. So we have time for a couple questions before, oh, no, Phil, okay. So Troy and Phil have been busily answering the extra questions in the chat. There's a question for Imke here from Thomas Haas. Is it true that Jupiter emits more energy than it receives from the sun?
Yeah, so it does emit about as much energy itself as that it receives from the sun, and that is caused still by after Jupiter formed, it slowly started to contract, and that contraction still emits energy to well, radiates that energy out.
Okay. I'm going to use my moderator's prerogative and ask you a question. Do you go to New Mexico to use the VLA to look at Jupiter?
Well, I mean, that's an interesting question, because in the past, we used to do that. Well, not really the observing. The observing was usually done, you write a script, and that's done by the astronomers on site. But when I started out in the 80s, you had to go to that observatory to actually reduce your data, because computers were, I mean, not very fancy, not very big. So you had to go to the observatory to actually do something with the data that they were taking for you. And there are many stories I could tell about that, but I won't do that here.
Okay. It looks like the questions are petering out. If there are any new questions, we can entertain them. There's one more question here. Since you mostly focused on radio observations, Imke, did you find anything new on Jupiter with James Webb that was not seen by spacecraft?
Yeah, that's a very interesting question. So we indeed observed Jupiter with the James Webb Telescope. So to our surprise, when we looked for the winds on Jupiter, I mean, the winds, we have seen that in the previous talks, can be traced by just looking at cloud features, tracking the cloud features. And usually that is done at the cloud level where we see the Hubble Space Telescope images. But with James Webb, we were most sensitive at some wavelengths at the haze layers just above the visible cloud layers. And in the equatorial region, we saw a very fast jet above the cloud layers. And that was not seen by any spacecraft or from the ground before, and was quite, intriguing. We had not expected that at all. A similar thing is actually seen on Saturn as well, above Saturn's equator, which was seen with the Cassini spacecraft.
Okay. Actually, we have a new question here that's really maybe each one of you could answer, which is from Judy Green. Are there any practical applications for any of the presentations? So why don't we just go in order here and start with Troy?
It's a great question. In terms of understanding the sort of how magnetic fields work more, I think that's quite useful a lot for Earth-based observations, Earth-based satellites, things of that nature. Um, Other than that, it's not totally clear in terms of specific practical applications. But I think part of it is just understanding more about what Jupiter is all about.
Yeah, and keeping in line with the title of this whole series, Basic Science Lights the Way. Basic science, sometimes you don't know what the practical application of it is until much later, and there's value in just understanding our universe. But Phil, can you think of any practical applications for your great red spot modeling?
Well, we're learning an awful lot about coherent and long-lived structures in the Jovian atmosphere. And as the climate changes on Earth, it's being dominated by these long-lived coherent structures that make, right, the polar vortex is coming down and gives chills to everybody. So I think that there's a lot of back and forth between studying what's happening in the layer where Jupiter has its clouds, which is called the weather layer, and the Earth's atmosphere. And large numbers of my students end up working in doing things like climate and climate change. And also, there's a lot of work that went into making these 3D numerical codes accurate and stable, and that's transferable to lots and lots of practical problems in engineering.
Imke, can you think of any practical applications of your Jupiter observations?
Well, I guess Phil already mentioned several of them. I think by studying the weather on Jupiter and on any planet, we also learn more about the weather on our own planet. And in particular, I think on what I sort of mentioned, storm systems, lightning storms, hail, seeing that on Jupiter, just we learn more about how these things happen and why here on Earth, in particular, the large hail stones that sometimes are visible, well, at least in dry areas in New Mexico and so on.
Okay, so I think maybe we have time for one last question, which I'm going to take myself. Joe Haller wants to know what would be needed to see even deeper into the atmosphere. Is that technically feasible? And I would take this opportunity to say we can send probes into planetary atmospheres. We sent a probe into Jupiter's atmosphere. That was my PhD dissertation topic. And the Galileo probe went down to 22 bars or 22 times the atmospheric pressure of Earth, that deep into Jupiter. So the next mission could go even deeper if we were to engineer probes to go deeper and be able to transmit their data back. So that's kind of the next step. And the only giant planet where we've sent a probe so far is Jupiter. So we really need to do the same thing at Saturn, Uranus, and Neptune to understand how the solar system formed. So I'm afraid that's all the time we have. Once again, thank you to the speakers for their enlightening presentations. And to close, I'm going to hand the floor back to Dean Kahn.
Thank you, Mike, for moderating, and thanks to all of our speakers for their informative presentations. It's always fascinating to hear about groundbreaking research emerging from our departments. I hope you will join us on Tuesday, April 29th at 5 p.m. for the next installment of Basic Science Lights the Way, where we will tackle some of humanity's biggest open questions like, are we alone? What are we made of? And what is the nature of the universe? Our researchers will weigh in on how each of them are chipping away at these mind-boggling mysteries. Please reach out if you'd like to learn more about anything we've covered. The video of today's session will be available at basicscience.berkeley.edu approximately 2 weeks from now. And you can always visit the website to watch episodes you missed. Thank you for being part of our efforts to uplift scientific research and education, connect curious people to science and ideas, and support discoveries, big and small. Until next time, stay curious, fiat lux, and go Bears.
Go
Thank you.
Bears!